day, everyone, and thank you for joining us today. My name is Dave Mercer, and I will be the moderator for our presentation. I'm a member of Fluor's Office of Technology, which focuses on using science and innovative engineering technology to build a better world. Our engineers, designers, and experts, that is our people, are at the core of our success. Thank you for joining us for an insightful webinar titled Nuclear Fusion, where we explore the future of electrical power generation through nuclear fusion. For decades, scientists and engineers have pursued the promise of fusion energy, a complex challenge that has recently seen significant breakthroughs. Advances in supercomputing and artificial intelligence are accelerating progress, bringing this long-sought goal closer to reality. In today's session, Dr. Fred Beranek will provide a foundational overview of fusion physics and the primary types of fusion reactor designs currently under development. The presentation will highlight the only fusion experiment to date that has achieved net energy gain. Additionally, attendees will gain perspective on the recent milestones and the current status of the global fusion industry. Fluor is uniquely positioned to support the fusion sector in designing and constructing infrastructure needed to convert fusion-generated energy into grid-ready electrical power. This webinar is ideal for professionals seeking to understand the technical landscape and strategic opportunities in fusion energy. So, Fred will kick off with a brief safety topic and then move straight into his feature presentation. Fred, now over to you.
Thank you, David. Very much appreciate the introduction. Appreciate the interest of all those attending the seminar. I hope you find it's of interest, even if you don't know anything about fusion or if you're a fusion aficionado. Hopefully something here will be new for you. So let's just jump right into the safety topic. And that is a question I'm often asked at fusion presentations because the press and the journal articles always like to proclaim fusion machines are hotter than the sun or as hot as the sun or bringing the sun to Earth. And so people ask, well, if you're bringing all that energy and heat into the Earth, why doesn't everything melt? So the answer is relatively simple, and that is that it is all in the mass. So if I have an example here, I have three large objects. One, let's call that a boulder. Say we have a boulder that we heat up to pick a temperature that makes sense, 150 degrees centigrade or so, very hot. If I stand well away from the boulder at 150 degrees, I will feel heat. It'll be warm. If I touch it, I'll burn myself. So if I have a smaller rock, indicated by that middle picture, the smaller rock, if I heat that up to the same temperature, and if I will feel heat if I get up close to it. Now I put my hands around it, I can maybe warm my hands, but I won't feel the same heat as being farther away like I do with a boulder. And again, if I touch it, I'll burn myself. And then if I have a pebble on the right there, and I heat that up to the exact same temperature, and I put my hands around it, I won't feel anything. There won't be any heat coming out that you can perceive. But if I touch it, I'll burn myself. So it's all in the mass. The sun is 10 to the 30th kilograms. If you don't like scientific notation, 10 to the 30th is a 1 with 30 zeros behind it. So it's a lot of mass. It burns 4 million tons of hydrogen a second. So it's all in the mass. That generates a lot of heat. So the fusion reactors, on the other hand, are in the micrograms of hydrogen, micrograms of fuel being heated up to those temperatures. So you'll hear 100 million degrees centigrade, but very, very little mass is actually at that temperature. So that's why nothing melts. However, if that plasma that's at that temperature gets out and hits the wall, it'll melt the wall. It'll damage the wall. So if you touch it, it hurts. If you're just a little ways away from it, you won't feel a thing. So, or won't feel much. 100 million degrees still is hot, but it won't melt things. So that's the safety topic, and hopefully answer a question many of you may have had in your mind. So the agenda for this presentation, I'll just introduce a little bit of nuclear physics. I gotta bore everyone with some physics, so you have a little basis for going forward. Talk a little bit about how fusion works, what's the basics of fusion. Then the major types of machines, as David mentioned, there are 50 different companies out there, all with different machines, but there are really a few major types, and I'll discuss very briefly the major types that are being looked at. The shot heard around the world, David mentioned the only fusion experiment that's actually created more energy out of fusion than went into creating it. So it's still the only one. I'll discuss that in a little more detail. And then what's going on in the world of fusion, the latest experimental achievements that have been published. How close are we getting? What are they showing? So these are all this year's results. So this isn't 10 years ago. This is what's going on right now. Discuss very briefly. So why is Fluor interested in this? We're not a plasma company. We're not a laser company. We're not a magnet company. So why are we interested in this? Talk a little bit about that. And then finally, the money. It's all about the money. These fusion companies are out there, and people are investing in the money or in the fusion companies, which is a very good indication that either the fusion companies are very good salespeople or it's about ready to start paying off. So we'll discuss a little bit about how that money is being invested, what it's looking like. So let's get into the nuclear physics part. So the part that everyone understands is the atom. I think this is a typical picture of an atom. It's if there are physicists out there, I recognize this is not a real picture of it, but it's a schematic that people have used for decades, and it shows the important parts of all we need to know here. The major part is the center of the atom called the nucleus. The nucleus is made up of two fundamental particles, neutrons and protons. Don't worry about the electrons. We'll ignore those for now because the electrons in the plasma are gone or they're elsewhere. And the plasma, when you heat up atoms high enough, the electrons all have too much energy and they dissociate from the atom. So you're left with a plasma of nothing but nuclei. The key things here in the nuclei that we need to know are the protons are all positively charged, neutrons are neutral. So that nucleus, if you look at it, it's just made of neutrons and protons. So the nuclei of atoms are all positively charged. And that is critical to the discussion of fusion and why fusion is difficult, because the nuclei are similarly charged, in this case, positively charged. The other key thing is that all the mass of this atom is in the nucleus. The electrons are about 1/2000th the mass of a neutron or the mass of a proton. Neutrons and protons are about the same mass. Electrons are 2,000 times lighter. So all the mass of the atom is in the nucleus. All matter is made up of atoms. So all the mass of matter is in the nucleus. So, and that is key. So the key is the mass, total mass in that nucleus, and how do we extract energy out of that? So years ago, probably 120 years ago, Albert Einstein was pondering issues like this, and he came up with this famous equation, E equals mc squared, which probably everyone has heard of. But maybe people don't realize the significance of it. But what he postulated was energy and mass are the same thing. That's a whole nother lecture, a whole nother discussion. We won't get into that here. Let's just realize here that the mass contains lots of energy. Mass times the speed of light squared. Speed of light is a big number. If you multiply a big number by itself, you get a really big number. So a little bit of mass times a really big number gives you energy. So the question always is, okay, So how do you get the mass? Oh, by the way, that's what's interesting. If you get on the internet, and there are all sorts of E equals MC squared calculators. It's fun sometimes to go to one and just plug in a mass, say a gram or a microgram or a tenth of a gram, and see what sort of energy is based on E equals MC squared, and see how much energy comes out of it. It'll give you energy in tons of TNT or megawatt hours or whatever it gives you. But it's fun to play with that. You can see tremendous amount of energy and very little mass. So the question is, how do I convert that mass to energy? So there are two ways to do it that we know of now. There's nuclear fission and nuclear fusion. So and nuclear fission is what we've been running the nuclear reactors on for decades. And that was kind of discovered or first, I would say. And that is when you take a very large atom, like uranium is typically used, and it divides into two other large atoms, smaller than the very large atom, but still two large atoms. And it releases energy. And based on E equals MC squared, the point is that the mass, when it's all done, the mass on the right side of that figure in the large atom plus large atom is less than the mass of the very large atom. So that mass difference is converted into energy. So that's one way to get mass out of the nucleus, or get energy out of the nucleus. The other way to do it is nuclear fusion. And that's when you take two very, very small atoms, generally hydrogen, which is the smallest atom. You smush them together, you combine them, and you form a new atom, which is slightly larger, but still small. And when you combine these, the mass at the end of that reaction will be less than the mass in the beginning. I may wonder why, if I split a large one in two pieces, I lose mass. And if I take two small ones and make a larger one, I lose mass. And I won't get into that, but you just have to trust me at this point. There are reasons why that happens. Now, if I take two large atoms and push them together, then I gain mass. So I lose energy. So just realize that the way fusion works is I'm combining two small atoms into very small atoms into a small atom, and energy gets released. And the figure below that will show one of the fusion devices I'll be talking about later that shows, and this will indicate that ring in the middle there of the torus that's white. And in the middle of that ring, in the middle of that white ring is the part that's really fusing and is 100 million degrees. So very, very small. And you can see that's quite a ways from the vessel, and the heat that's generated there will not melt the vessel. So those are the concepts of how do I get energy out of the mass of a nucleus. So let's go to talk about, so how do you make fusion occur? Why is it hard? Why is, David said it, decades and decades of research into this. Well, let's look at a box. Say we had a box on the left there of nuclei, and they're just floating around, bouncing around, traveling relatively slowly, pretty fast, in our classical sense, but relatively slowly in the nuclear sense. And they just travel around, they bump into each other and ignore each other. Remember, these are all positively charged particles, and positive charges repel. So if two come close to each other, they push each other away. So it's hard to get them combined. And if you saw on the previous chart, I need to make those nuclei combine. I need to make them squish together and react with each other. But they don't want to. They want to push away from each other. So let's say I have a box of those things and they're bouncing around. One way to get them to collide more frequently, and therefore have a better chance of colliding together, is I increase the density, which means one way to do that is to make that container smaller. So if I take those same number of particles and confine them to a smaller volume, I've increased the density. And now you can see, if you look at the figure, they're more likely to bounce into one another. They're more likely to collide. If they're more likely to collide, they're more likely to react. So that's one thing. You've got to get the density of these particles increased to very high values. The other thing that you want to do is increase the energy, increase the temperature of these nuclei. So you have to heat them up. Because if I heat them up, now the particles will be traveling faster, they'll collide more, they'll collide with more energy, and they're more likely to overcome the repulsive force, more likely to react. So I want to increase the density and I want to increase the temperature. And then I want to have them there as long as possible. The longer they're there bouncing around and colliding, the more likely they are to fuse and create energy. The product of those three terms, density, temperature, and time, is called a triple product. And if you look at fusion, read about fusion, you may hear about those, read about them. It's something, there's a physicist named Lawson who years ago came up with this and said if it reaches a certain value, the triple product reaches a certain value, then you'll have fusion ignition. So all these decades of research have been trying to come up with a mechanism to increase the density, temperature, and time to a level that meets that Lawson criterion. And that is what's been complicated. So the question is, what do we use for fuel? We've always talked about using hydrogen. And this figure may look a little complicated. I'll simplify it for you, but it's got some very interesting information. So let's just look at the blue curve first. It's labeled DT, which is a deuterium and tritium. Those are two types of hydrogen. Deuterium has one proton and one neutron in the nucleus, and tritium has two neutrons and one proton in the nucleus. So they're both hydrogen, both light, and that's what most companies are thinking of using for their fusion fuel. If you look at the y-axis going up, that is increasing the probability of reaction. Don't worry about the numbers. Don't worry about the terms. Just recognize as I move up that curve, that says my reaction probability is increasing. On the horizontal axis, it says center of mass energy. Again, physicists like to talk fancy. Let's just call that temperature. So as I go along the bottom of the axis, I see that value of 10. That's 10 keV on this slide. That's roughly equivalent to 100 million degrees centigrade. So, and 20 is 200 million, 100 to be a billion degrees centigrade. So in this case, temperature and energy are interchangeable. So if you see on the blue curve, it shows that at lower temperatures, let's say 100 million degrees, then the probability of a reaction of deuterium and tritium is much higher than any other fuel type. That's why most companies are going after deuterium tritium. So because at 100 million, it looks like it's maybe 50 times greater chance of probability than deuterium and deuterium, which is the green curve. And the other curves don't even show up at 100 million degrees. So if I can get to 100 million degrees, the DT mixture is more likely to fuse than any other mixture. That's why most companies are focused on deuterium and tritium. And if I can make it higher and higher temperatures, 200 million, 500 million, you see that curve keeps increasing, much larger likelihood of colliding and igniting fusion. Now, the downside, the reason some other companies are looking at other fuels is deuterium and tritium reaction generate a lot of neutrons. Neutrons are not good for the materials trying to contain the plasma. It damages the first wall. And so you would like to have a reaction to not generate neutrons. Plus, tritium is not naturally occurring, so you have to manufacture the tritium, which you do in the fusion machine itself. So you take those neutrons and generate tritium from those in a blanket surrounding the fusion machine. But the neutrons have to pass through the first wall and cause damage to the first wall. So that's the problematic. That's the problem with DT. Let's just jump down to the yellow curve. I'll say that's the holy grail of fusion. That's proton boron 11. It's a kind of a gold yellow curve. And the problem with that is you have to get up to 1 billion degrees. And even at 1 billion degrees, the likelihood of fusion is 4 orders of magnitude less than DT. If you can get that reaction to occur and get up to maybe 500 billion degrees, now you're up in a really high reaction rate for proton and boron 11. So what's the beauty of that? The beauty of that is it creates no neutrons. So the product of plutonium and boron are 3 alpha particles or 3 helium nuclei. So no neutrons. So you don't have any neutron jams to the wall. You don't have to manufacture tritium, which is an engineering barrier, an engineering concern that you have to factor into fusion machines now. Proton is just a hydrogen nucleus. So it's really hydrogen and boron, both very available. So there are companies that are striving for that, ignoring the DT and DD and other types of fusion fuels, and looking at that, because that is if you can get to there and make that happen, then these other fuel types will kind of pale in insignificance if you can get to there. So great type of fuel. But you can see that's why companies are trying different fuels. They have different reaction rates at different temperatures. And depending on what conditions you can create, depends on what fuel you can use. And some have advantages over others. So how do I do this? How do I make these fuels react? There are two major types of fusion reactions, or fusion containments. One is magnetic and one is inertial. So here we'll talk about magnetic confinement. I would say the vast majority of the companies are working on some sort of magnetic confinement. Most are using the type of picture on the left, the tokamak. Tokamak is a torus. The blue parts of that tokamak there are magnets. Those are high temperature superconducting magnets. So they're running at maybe 20, 30 degrees Kelvin. So they have to be cooled way down to carry the amperage necessary to get the magnetic fields. But the way this works is that these magnets create all sorts of twisted magnetic field lines inside that purple area. Let's say the purple area is the plasma that's in that tokamak that goes around and around and around. And these magnets have to contain that so the plasma does not interact with the wall, and also so it squeezes together to make those reactions occur. And then you heat it up to 100 million degrees, and that's pretty easy to do. So you heat that up, you squeeze it with the magnetic fields, you keep the magnetic field, keep the particles away from the wall so it doesn't cool off the plasma. And then hopefully you can get the density high enough and you run it long enough. The idea is then you'll get fusion ignition and self-burning, and you'll be able to get energy out of that. The difference between the tokamak and on the system on the right, called the stellarator, is the tokamak has a center column you see. It's a blue column. It's called a solenoid. And for the tokamak to work, that solenoid, you have to slowly increase the current in the solenoid. Electric current increases, and as that current is increasing, that forms a plasma current in the tokamak, in the toroid, which makes that system work. But once you slowly increase that current, at some point you got to turn that current off and start over again. So tokamak is technically a pulsed machine at this point. Pulses can be minutes to hours, but at some point you have to turn it off, let the solenoid de-energize, and then start the current up over again. So that pulse is not good if you're trying to put baseload power out there and don't want to shut your grid down lots of times. So you have to store energy on these so you keep the load to the grid constant. The stellarator, on the other hand, is I'll just say it's a similar concept, lots of magnetic fields, but they form their magnetic fields by twisting their magnets. The tokamak forms it by regularly shaped magnets with fields combining to form a twisting motion. For the stellarator, you get twisted magnetic fields in the middle by twisting your magnets. So therefore, you don't need a solenoid in the middle, so it can run at steady state. You can just turn that on and let it run. Now, those have been studied. They started being studied 80 years ago. People stopped looking at them because of the manufacturing process for making those magnets. They're just very much too difficult to manufacture. But now with advanced manufacturing techniques and some other companies that have different ideas on stellarator geometry, now it's come back to the fore because you can run them steady state. So there are several companies that are advancing the stellarator concept. And so those are the two major concepts of how to make fusion and magnetic confinement. There are many other types that are out there, but these are the two major ones. The other type of confinement is inertial confinement. And I'd like to thank the folks at Elsevier's for allowing me to use the figure on the left. So this shows schematically for inertial confinement, you use a very, very small hydrogen, deuterium, tritium target. Very small, and I'll show pictures of them later. but very small capsule. And instead of having magnetic fields and combining a gaseous plasma, you take a frozen deuterium and tritium, and you blast it with lasers or ion beams or some force. The idea is to compress that capsule to such a high density that you reach the triple product. So your temperature and density, your density is extremely high. Your temperature is high, your time not so much, but still the triple product, the density times temperature times time can achieve the Lawson criterion. So the idea here is you drop pellets in from the top, you hit it with lasers, it fuses, it delivers energy to the blanket you see in that brown cylinder, brown device around the outside with the disc, and then you have coolant running through that to the steam generator. So that's generally how inertial confinement works. On the right is a picture of the inertial confinement facility at Lawrence Livermore Laboratory, the National Ignition Facility, where the tests I'm about to talk about took place. And you'll see there the lines going in, the laser lines going in, attacking the target. Now that's a experimental facility, so that you don't shoot targets into there. You put them on holders and you just put it out there, and they run that once every few weeks. You can get a shot in right now. So it's not a system like on the left, and for a power plant, you'd have to drop those in at maybe 10 times a second. So totally different devices, but it just shows you schematically what those look like. So let me get into discussing the inertial confinement fusion a little bit more, because that's the only one that's been proven so far experimentally that works. So you'll see on the next slide, you'll see what's called a holorum. And that's very small. That's just millimeters in length. So that's a very, very small gold holorum. That's what they use for the experiments at Livermore. The deuterium tritium pellet is suspended in the middle there, and then the lasers come in through the holes at the end of that cylinder and impinge on the walls to create X-rays that collapse the pellet. So I just wanted to show that to give you a little scale. I mean, that's very, very small. The next slide will show you a little more in detail of what that looks like. So the 1 centimeter holorum is on the left, and you'll see the laser beams coming in at angles. It comes into the 2 holes at the end of the capsule, and then it hits the walls of the holorum and creates X-rays. And that's important. So the lasers in this technique, that's called indirect drive, do not hit the pellet. They do not hit the pellet. They hit the walls of the holorum. The holorum generates X-rays. The X-rays uniformly attack that pellet. In the next slide, in the next picture over, you'll see the pellet is blown up, expanded there. That's a frozen deuterium tritium. You see a little shell around the outside, and deuterium tritium gas in the middle. And the picture, the red dot in the middle, shows when you hit that with the X-rays, it compresses to that size. The red in the very middle there shows where it's actually burning. Well, it's figuratively, I mean, schematically, this isn't a photograph, obviously, but schematically, you'll see a very, very small bit of that laser burning, or the deuterium and tritium burning. That's what causes your fusion. That's what results in your energy gain. On the right, you'll see that little part expanded out. And so the compression heating, the outside layer of that the sphere ablates. It compresses that into a very, very high density pellet. It heats up. It's the fusion reactions begin. And the alpha particles are emitted by the fusion reactions heat up even more than just was done by the compression. So that's what gets you your net energy gain, is the alphas have to heat up some of that fusion fuel to create more heat than went in by the compression heating. That's how you get your net energy gain. So just the very, very middle of that sphere will have ignition. So the fuel in a DT, in an inertial confinement fusion, maybe only 10 to 15% of the fuel in that pellet actually burns. The rest gets, when this heats up, it expands. So those unburned deuterium and tritium get released into the chamber. It gets sucked out. You have vacuum pumps sucking them out. It gets recycled to create more pellets. But but only about 10 to 15% actually heat up and burn in that technique. What I find interesting is a picture on the next slide of the laser pulses. One thinks of a laser pulse, just boom, it goes. That's not true. Here, you saw different cones of lasers coming into that hall room. This is the type of shaping they do on those lasers. You look at the red curve, that's the outer cone of lasers. The total time there is 10 nanoseconds. That's 10 billionths of a second. The laser pulses in power there are shaped. So the first quarter of a nanosecond, half a nanosecond, is flat, then it rises, then it's flattened out again, then it goes down again for a nanosecond, then it goes back up, and then for 2 or 3 nanoseconds, it's at its peak, and then drops back off. So it's not just a pulse, and then there's another layer of pulsing. So it's pretty intricate. And these decades of work they've been talking about, and years of work, are shaping these pulses to get just the right shape and magnitude that you get the most efficient burn. So that's critical. And now with, as David mentioned, the supercomputers and AI, they can do this much faster now. But let me take you, draw your eyes to the left of that curve. In December 5th, almost 3 years ago now, is when the very first fusion reaction that created more energy than went into it was generated. And that was the shot heard around the world. It was amazing. And 2 megajoules of laser energy delivered to the hall room, 3 megajoules of fusion energy were generated. So that's not a whole bunch, that's not going to light New York City, but it's the first time ever. It's a huge, huge event. And of course, people point out, well, the lasers actually used for the test consumed 300 megajoules. So you didn't even create enough energy to power the lasers. Well, that's fine. That's right. I mean, it's a test that the lasers were not designed for this. The lasers that'll be used for actual power plants will be more like 10 or 15 megajoules. So they've made huge advancements in lasers that'll solve that issue. So that was a huge gain. Now the question was, can you do that again? And so we showed later that indeed over the next 3 years, they reran similar tests like this, and they got on the next slide. You'll see we've got now 8 successful tests. So these are the tests and the dates. The laser energy in by the red bars, and the fusion energy out indicated by the gray bars. So they've shown 8 times they've been able to do this. The last time, this past April, they had a huge target gain of almost 4. So you need about 10 to 15 to be able to power all your energy sources, all the supplies you need, what we call engineering break even. Once you make a high enough gain to power your machine itself, anything more than that, you can sell as electricity. So that's quite an achievement in 2.5 years to get that gain now up to 4. So that is working. They're still playing with the pellet, playing with the lasers, and trying to increase that even more. So that's fun to watch, to see each time they publish something that says, oh, we got a better gain. And so there are some companies that are using that technology for their power plant. And so that, to date, that's still the only experiment that's achieved net fusion energy. So let's check some other achievements for the past years, or this past year. So let's get back into the magnetic confinement. There's a machine called HL3 in China, and this experiment was earlier this year. And they used a deuterium-tritium plasma. Most places experimentally are using deuterium-deuterium because it's not radioactive, easier to handle. But in this experiment, they exceeded 160 million degrees Celsius. So these temperatures are being achieved. This is a tokamak machine. All they said was the fusion triple product rose significantly. Don't know what that means. Don't know well, I know what it means. It means it went up significantly, but I don't know close to the Lawson criterion, still way away. I don't know. So the temperature is good. Temperature puts you way up on that DT curve that I showed you. Allows a good reaction rate, but you don't know the density and you don't know how long they held it. It could have been a millisecond. It could have been 10 seconds. I don't know. So, but the plasma temperature of 160 million degrees was a fantastic achievement, and that's the Chinese reactor. So back in the European side of the world, in France, they have an East tokamak. Now in France, they have a West tokamak. They also use deuterium tritium plasma, and they got up to 50 million degrees centigrade, or Celsius, 50 million. Not the 160 million, but 50 million was on that curve I showed you. That was a reasonable reaction rate at 50 million. But they were able to maintain it for, looks like 20 minutes, 1,300 seconds. So this experiment, they were trying to see if they were trying to exceed the duration for holding a high temperature, high density plasma together. So the East tokamak earlier this year, I forget what it was, 1,000 seconds or 900 seconds. I forget exactly what they had published, but France, I think this was in May timeframe, came out and said, well, we did better. So we can see these experiments one by one are getting closer and closer to where you want to get. Another experiment that was in May of this past year was a stellarator. So this was a world record for triple product. So I couldn't find in the literature what the triple product was, how close to Lawson criterion it was, but apparently this is the Windelstein stellarator. This is a stellarator made in Germany. It took a long time to make, but it's functioning. They did make those weird shaped magnets. Tight tolerances, a very difficult construction process, but it's running. So in May this year, for 43 seconds, they achieved 20 million degrees Celsius. And the time must have been long enough that that product of 43 seconds and 20 million degrees and the time set a new world record for triple product. So yet another experiment that is getting closer and closer to break even in magnetic fusion. So it's exciting times. And if all three of these were this year. So by fall this year, if I gave this talk, there'd be something else to present, a new record. So it's very, very exciting time as they approach break even. So why does Fluor care? Fluor is not a magnet company. We're not a plasma company. We're not a fusion company as such. So let me give you a picture. This is a power plant that is conceptual. This is there's an experiment, a big experiment going on in France called ITER, International Thermonuclear Experimental Reactors, experimental facility, still being built. Very, very large facility designed to provide experimental data to give to fusion companies to support their research. So the follow-on to that experiment will be a power plant they call DEMO. And DEMO takes the ITER technology and makes a power plant out of it. So they have this conceptual power plant. If you look in the kind of the center of this picture, maybe a little bit to the left of center and a little bit to the lower part, you see an upright blue column. That's the solenoid we talked about when I showed a picture of a tokamak earlier. So that machine there is a tokamak. You see the green magnets that circle that. So that's the size, conceptually, of the tokamak. Everything else around that, the rest of that building, is something that Fluor would design. So we don't know tokamaks. We don't know the magnets, the cryogenics, the tritium separation. Other companies would do that. But Fluor's involvement would be to design, and that's something we've been doing for decades on power plants, around the world. We're good at that. So we don't really care how the heat is produced, be it fusion, be it diesel generator, be it fission reactor. We design how you get that heat out and transfer it to electricity, to the grid, and all the support facilities that go with that. So that is Fluor's interest, not in the machine itself, but in being able to design the rest of the facility, the rest of the building. So that's what we need to do. So, how close are we to? What are there any other barriers to fusion that we see out there? The challenges to that these companies are working on? Yes, there's still some engineering challenges. Plasma instabilities in a magnetic plasma or inertial confinement. It happens very quickly. Plasmas are like, I think I've shown pictures before of holding Jello between your hands and squeezing the Jello, and it comes out between your fingers. Well, something like that happens in plasmas too. When you have the magnetic field squeezing the plasma, it'll hold for a while, then all of a sudden something will bloop out and it cools off and you lose the plasma. So they keep working on that. Materials, I talked about the neutron damage to materials. They're trying to develop materials that sustain neutron damage better than others. Probably the first reactors will be regular steel, and you just have to replace the vessel more frequently. Tritium extraction, I talked about having to make tritium in the blanket. You have to extract that tritium from the lithium, circulate it around your system, and get in a form that you can refuel your reactor with. So companies are working on that. Laboratories are working on that part. Pellet design for initial fusion. I talked about the pellet. We keep trying to, they keep refining the design to increase the gain. How do you fabricate these things? They need 1 million a day. So you have to fabricate them obviously very quickly. So that sort of design and work has to be completed for inertial fusion. The laser design, I talked about the pulse shape. They keep working on those to get a better pulse shape to increase the gain. Supply chain, there is no supply chain for fusion systems right now. So standardization would help, but the problem is all these companies are different. So the poor suppliers, one company wants one type of magnet, another company wants another type of magnet. So the supply chain is going to be problematic. How do you gear up to make all sorts of different pretty high-tech devices? Advanced manufacturing will help there, but that's a barrier that has to be overcome. And at the end, you can probably do all this stuff, but how much does electricity cost? It all comes down to that. You have to make sure you get all this stuff done and have a reasonable cost of electricity, which is, again, what Fluor does. On the next chart, we'll show you some of the worldwide investments. You see there's about $10-12 billion invested in fusion, mostly in the U.S. China, the government has put in a lot. The rest of these, a lot of these are private funded. So the U.S. has about 38 of the 68 companies that are being funded. But so it looks like U.S. and China are the two big players in this. The next will show investments in fusion. This was provided by Fusion X. We appreciate that. You'll see the investment by year. You see this huge pulse in 2021, and in 2025, another significant amount of investment. It's growing. The entrepreneurs are excited about it, and so we'll see what happens. But money's coming in, and so it's an exciting time to be here. Finally, we're looking at who's building a plant? Who's actually building a plant? Here's what we've got so far. This is 3 plants are being discussed. Type 1 Energy is still a pilot plant. They're a stellarator facility. They're talking about building one in Knoxville. Commonwealth has agreed with Dominion Energy in Virginia to build a power plant called ARC. And then they've got takers. They've got Google and Microsoft both to buy energy from that. So they're off and running. And then on the other side of the country, Helion has a contract with Microsoft. They're going to build a plant. That's neither a tokamak nor a stellarator nor inertial confinement. I won't get into that one, but it's another magnetic inertial kind of combination design. But they're going to build one in Malaga, Washington. And they do have a contract with Microsoft for 50 megawatts. So there are 3 plants that are actually being on the drawing boards going forward. So that's all I've got right now. I think we've left some time for questions if people have sent some in.
All right. Well, thank you very much, Fred. That was excellent and very, very, very interesting. We did receive a couple of questions from the audience. And to our audience members, as a reminder, please make use of the Q&A tab to ask any questions going forward here. So Fred, the first question that has arrived here is this. Do you believe fusion on the grid is feasible within the next decade? Your thoughts on that?
Yes. I'm just trying to think decade, 2035. Yes. From what I go to a lot of the fusion meetings, fusion conferences. Of course, everyone's optimistic about their concept. But when you see the NIF, National Enrichment Facility, with break even, I mean, that you see, and you understand that can be that's actually proven technology, and you see that the plans companies have made for increasing laser efficiency. I talked about that a little bit. I mean, significantly huge laser advancements with a supercomputer. The target gain you see in 2 years, significant target gain. So things like that, how you make $1 million a day, they're working on that, and that'd be to me a little problematic to make that. But there are things they're looking at to achieve that. There won't be a gold hull room. They'll use lead. So trying to get the cost down on things like that. So I really do see that achievable in the decade. On the magnetic side, of course, the main player there is Commonwealth. They're building their pilot facility. It's coming out of the ground. I saw it maybe 2 years ago. I expect to get that started up next year, finished next year, 2026. So that, and they've got models, they've got peer-reviewed models that say that will work, supercomputers, advanced modeling, and then these other areas that you don't read about too much, the other types of fusion machines, the Helion machine you don't hear too much about, but they're going to, they must know something because they've committed 50 megawatts to Microsoft in 2028. So that's well within the decade. So I think we have enough shots at the. Another way of looking at it, there are 50 people shooting at it. One it will be bound to hit. I think in the next decade.
That's great. Well, we appreciate your perspective on that, Fred. It's very, very valuable. Thank you. So here's another question from our audience. Is there a method that utilizes a small-scale fusion reaction to initiate a larger fusion process?
I don't know of any. There are, I'm thinking of, I hate to get into the weapons world, but they do use fission reactions to create fusion reactions. I have not seen, and I've seen there are some companies out there still working on room temperature fusion. If you remember, I forget when it was, been around too long, probably in the 1980s or so. Cold fusion, there was a discussion of cold fusion. Some people in some university thought they had saw fusion neutrons, thought they saw 14 MeV neutrons from fusion reactions going on at room temperature. Turned out it was not true. But there are people that are using certain metal structures, palladium, I believe, possibly, to put deuterium and tritium in and have them, the molecular structure in the metals, bring the deuterium and tritium close enough together at room temperature or low temperatures and create fusion reactions. But I don't know of any system using a small fusion reaction to create a larger fusion reaction. There are concepts to use fusion machines with a fissionable blanket. So you don't have to make energy, you don't have to have break even from your fusion machine, but it generates enough neutrons to irradiate a fission blanket. So it's what they call a hybrid system. You initiate it with fusion reactions, you create neutrons, and then you have a fission reactor essentially around a fusion reactor. So I've seen those conceived, but not a fusion reactor. I've not seen that.
Okay, very well. Thank you, Fred. Okay, the third question here we have relates to power generation out of the tokamak. So when I read this question, maybe, Collie, could we move back to slide number 22, maybe? Because it could be a good, useful reference for Fred when he replies to this question. And Fred, maybe you could give a description here, but the question is, where is the proton exchange / steam generation facility installed? I think what they're asking is relative to the tokamak reactor. So I don't know if this slide might give you a little bit of context and, where you could maybe suggest the steam gen facilities are installed, but I thought flashing this up on the screen may be of assistance to you.
Yeah, that's fine. So let me cover since no one's built one of these yet or designed them yet, let me explain the heat transfer mechanism in a tokamak. We talked about the blanket, and the blanket in a tokamak will be the variety of metals being discussed or materials being discussed. It won't be water. It won't be filled with water. You need to make tritium. So it'll be some sort of lithium compound. So the beauty of this having to make tritium and with the neutron makes tritium and generates the heat. So you get double bang for your neutron there. It'll make tritium in that blanket, deposit its energy. It slows down, it scatters around, and so it deposits all its energy into that blanket system. Most likely, these will be liquid lithium blankets, either liquid lithium, a common compound that I've seen around is something called FLIBE. It's a fluorine lithium beryllium compound. The fluorine and beryllium providing certain characteristics that are very valuable. So it'll most likely be liquid. The liquid of the lithium will be circulated out of that system through a heat exchanger. And so it'll be piped out of the blanket through a heat exchanger. Now, the question on the heat exchanger is, that first heat exchanger is, will it be a heat exchanger to water, which would turn to steam? That'd be your steam generator. Or some places will convert it, will transfer that energy to helium, a helium loop. The reason you do that, it's less efficient because you have to go from FLIBE to helium, then helium to water later on to generate steam for your steam turbine. But the fact that you want to keep lithium and water really, really far apart if you can. As most people on the call probably recognize, you get lithium and water together, and it's a bad day. So from the accident analysis perspective, from the NRC, the way they would look at it, lithium water heat exchanger could be problematic. So you most likely go to lithium, that'd be heat exchange. Then you got to take the helium to another heat exchanger to the steam generator. And so in this chart that he's showing, I assume I haven't gone through this chart all that much, but I think the blue things on the right are your turbines. So somewhere maybe that cylinder to the right center might be a heat exchanger of some sort. So a steam generator would be about in that area, though. So the lithium would come out of the tokamak into a heat exchanger that would convert either to the helium or the water. If you get her to helium, that'd be nice because then you can get that out, get into a non-radioactive side of the plant where you might be able to have your steam generator, or at least a less radioactive area, to create the steam for the turbine. So the steam generating mechanism would be in that general vicinity.
All right. Wonderful. Thank you very much, Fred. Here's another one that I think you touched on briefly in your most recent reply. Are the safety or protection systems for a nuclear fusion power plant similar or different when compared to a conventional fission nuclear power plant? Any thoughts on the safety systems between the two.
Oh yeah, and that's the beauty of fusion and why the fusion industry unanimously, I keep using the term fusion reactor, and I've got to get that out of my lexicon because I've been doing it for 40 years. So it's hard to stop. We call them fusion machines because people associate the word reactor with a fission reactor. They're two totally separate devices. So a fission reactor is very safe, and I always hate to draw the comparison because people go, oh no, fission reactors are unsafe. They're not, but they have a variety of safety systems. They have a safety system that shuts the reactor down. So if it's operating and something happens, it doesn't shut down automatically. It has to have safety rods dropped in and control rods driven in to shut the reactor down. Now, the newer ones, the SMRs, will be totally different. They'll have different safety systems. But you have to cool the core in a fission reactor. That's the key thing, is you have to cool the core even after it's shut down. It has to maintain cooling. In a fusion reactor, it's hard enough to get it going. If it trips off, it's off. It's done. It just stops. The fission reactor has all the fuel it needs essentially for 30 years in the core. Now they refuel every 18 months to 3 years or 5 years, depending on the reactor. So they do shuffle core around, but there's enough fuel in those things to run for a long time. So that's available to be burned. If something goes wrong, that fuel is already in the core. In the fusion reactor, you're constantly refueling. It's like a car engine. You have to keep putting gas in and to get it to keep going. So if something happens and the fuel stops being injected, the fuel that's in there will burn up in a microsecond and poof, you're done. So the safety systems for a fusion reactor will be focused on the tritium inventory. Tritium is a radioactive material. You don't want it to get out. And so all the safety will be to make sure the tritium in there can't get out through the stack, can't get out through the walls, can't get out in accident situations. So the safety systems, which haven't been designed yet, will focus on maintaining the tritium confinement. And that'll be it. The rest of the system shuts down on its own, even if you don't want it to sometimes.
All right. Very well, Fred. Well, I see we're just a couple of seconds away from the top of the hour here. So it looks like that's all the time we have for questions today. Thank you again, Fred, for what I would say to be a very informative webinar and the time that you spent both today with us and in preparation for our event today as well. Also, thank you to our audience for attending today. It certainly has been a pleasure being your moderator. So please continue to stay informed of these events by visiting the Innovation Builders page on Fluor.com or following our social media channels using hashtag Innovation Builders. If you'd like us to send you an email notification of future webinars, please email us at innovation.builders@fluor.com with opt-in in the subject line. We appreciate your attention and thank you again for dialing in today. We will send out a compiled list of the Q&A shortly, along with the notification that the webinar recording is available for replay on Fluor.com. If you have any questions or require additional information, please email innovation.builders@fluor.com and someone from our team will get back to you. From all of us at the Innovation Builders team, have a safe day and thank you.